Hello and welcome back to another video on how to solve a problem from the Introduction to Electrodynamics by David Griffiths. Here we have a 4-part problem, problem 5.20, and it's asking us to find the density of mobile charges in a piece of copper assuming each atom contributes one free electron. So we know the density is defined as charge per unit volume. Since we are assuming each atom contributes one free electron, we got to solve this in atomic level. Here we could break this up into charge per atom times atom per mole times mole per gram per volume. Right? So we're splitting it up like this, and this will allow us to use a formula using physical constants here. So this would be our charge of the electron. This would be our Avogadros. This will be our atomic mass. And this will be our density of the copper. D. Right. So with this, we are allowed to use the formula E n times 1 over m d. And these are simply just constants, so let me just write them out real quick. Right, so I've gone ahead and written down these constants here. So now we can just plug them in and find our density value. So, simply as our charge of the electron, 1.6 times 10 to the negative 19 coulombs. Our Avogadro's number, which is 6.0 times 10 to the 23 mole. Oh, looks like I'm running out of space here. Oop, let me just move this down here. So now we have our atomic mass, which would be 1 over 64 mole. And then our density of copper, which is 9.0 centimeters cubed here. Upon evaluating this, we will end up with 1.4 times 10 to the 4 coulombs per centimeter cube. Right, for part B, it's asking us to calculate the average electron velocity in a copper wire 1 millimeter in diameter carrying a current of 1 amp. So, for this problem, we have our diameter of the copper, which would be 1 millimeter. This will equal to 10 to the negative 3 meters, and which makes our radius equal to 5 times 10 to the negative 4 meters. So, using this, we could find our area, pi r squared, times 10 to the negative 4 squared, and this will give us a value of 7.85 times 10 to the negative 7. Our current density is expressed by J equals to I over the area, which is why we calculated the area. So plugging in our values for 1 amp over our area, which is 7.85 times 10 to the negative 7 meters squared. This will give us 1.2738 times 10 to the 6 amps per meter squared. So the relationship between the current density and drift velocity V would give us the equation of J equals to rho V. Manipulating this equation, V will equal to J over rho. And plugging in these values, since we know these from the previous part, rho will give us 1.4 times 10 to the 4 coulombs per meters cubed. And we know our current density, which is 1.2738 times 10 to the 6 amps per meter squared. This will give us a value of 9.1 times 10 to the negative 3 centimeters per second, which in fact is a snail's pace. Part C, which is what is the force of attraction between two such wires 1 centimeter apart. So, two such wires, I'm assuming that the current is going to be the same of 1 amp from the previous part. And so using that, we can use the force per unit length equation we are given from equation 5.40. which states the force of equation, force per unit length equals to the permittivity of free space over 2 pi times our currents, I1 and I2, over the distance between them being apart. So all we need here is our permittivity of free space value, which is just 4 pi times 10 to the negative 3. And can't forget our units there. So we just plug that in real quick to our equation. 4 pi times 10 to the negative 3 over 2 pi times our current, which is 1 amp for both wires, over the distance of them being apart, which is 1 centimeter. And this will simply just cancel out the amps here. And so this will simply just be 2 times 10 to the negative 7 newtons per centimeter. Right, for this next part, it's asking us if you could somehow remove the stationary positive charges, what would the electrical repulsion force be? How many times greater than the magnetic force is it? So for this part, we are needing something from the previous chapter, which is the electric field of a cylindrical charge. And that would be equal to E over 2 pi epsilon naught over lambda over D. And our lambda is our linear charge density. Knowing this, we know how to calculate force, which is force equals to the charge times the electric field. However, to calculate force per unit length, force per unit length, our formula here is lambda times our electric field. So putting these two together, we get our electrical repulsion. Knowing this, we can express the force of electrical field between two wires, and this is written as Fe equals to 1 over 2 pi epsilon naught lambda 1 lambda 2 over D. Again, since there is two wires, we get two lambdas, and here lambda 1 equals to lambda 2, which equals to I over V. Plugging that in, we get 1 over 2 pi epsilon naught I over V over D. We can take out those 1 over V's, so we could turn this formula into 1 over V squared, 1 over 2 pi epsilon naught I1 I2 over D. So moving along, we're going to be using the relationship of C squared to 1 over mu naught epsilon naught, which will give us our needed relationship of 1 over epsilon naught equals to mu naught C squared. Since we have a mu naught here, we can replace this part of the equation, and we will have Fe equals to 1 over V squared. We're going to be using this as mu naught C squared over 2 pi I1 I2 over D. So we know the magnetic force equation. That is simply F mag equals to mu naught over 2 pi over I1 I2 over D. So we could simply divide these two to get our ratio of forces, which is simply Fe over F mag, which equals to 1 over V squared of mu naught C squared over 2 pi I1 I2 over D over our mu naught over 2 pi of I1 I2 over D. And this will simply just become c squared over v squared. Now we know the speed of light is 3 times 10 to the 8 meters per second. We'll be converting that into centimeters to match everything else. So it'll be 3 times 10 to the 10 centimeters per second. Alright, knowing this, we could plug it into our ratio of the forces equal to our 3 times 10 to the 10 centimeters per second over 9.1 times 10 to the negative 3, our Snell's pace we solved previously, squared. And the ratio of the forces will equal to 1.1 times 10 to the 25th. Knowing this, since we know the value of Fmag, we can move this to the other side. Fmag was solved in part C, so our value for Fe will equal to 1.1 times 10 to the 25th times our Fmag, which would be 2 times 10 newtons per centimeter. And we will end up with 2 times 10 to the 18 newtons per centimeter.